Now let's move on to doing some indefinite integrals with substitution. So we did one example last time on Wednesday. Let's do some new examples. So here's our first new example. Integrate, say, t times e to the t squared dt. Notice this is an indefinite integral. I'm after an antiderivative, so I need to make sure I add the c. Definite integrals are numbers. When you've got definite limits of integration, they're functions if I make one of the limits of integration a variable. Indefinite integrals are families of functions with a plus c, where c can be anything. Now, you could probably guess the answer here. In fact, let's do it together. I'm looking for a function whose derivative is t times e to the t squared. The answer's got to involve an e. And if you think about it, it would have to involve e to the t squared. So as a first guess, you might guess e to the t squared. That's a guess. And it's a guess that's not too far off. From the chain rule, you get e to the t squared times the derivative of t squared, which is 2t. Almost this function, except for the 2 in front. Well, you can easily modify your guess to get the right answer. 1/2 e to the t squared must be the right answer, plus c. Now, when you multiply by 2t, the 2's cancel, and you can write this as t e to the t squared. So you can certainly guess the answer. But I want you to use substitution here, including on your homework, because substitution sometimes really is necessary. Guessing is sometimes too hard. We are going to do an example where guessing is too hard. So here again is the technique. Introduce a new variable. Many books call it u, and it's fine if you use a u. Our book calls it w so that it doesn't get mixed up with integration by parts. You want to let w be something in this integrand function whose derivative is also in the integrand function, at least up to multiplying by some constant. The derivative of t squared is 2t, which is almost there, except I don't see a 2. There's a couple ways that can be compensated for. One is I could put a 2 in there. But if I do that, I also have to put a 1/2 in there and maybe bring the 1/2 out in front. And that's a fine way to do it. You also, after solving for dw in terms of dt, in this case getting 2t dt, you could multiply both sides of this by a 1/2. And that would mean you replace t dt with 1/2 dw. Now, some people are sloppy and they just write dw equals 2t instead of dw equals 2t dt. Don't be sloppy. It's worthwhile to not be sloppy. It's worthwhile in terms of getting right answers, especially for harder problems, as we will see. I skipped a step compared to last time. I skipped the step where I would write dw dt equals 2t, and then I pretend I multiply both sides by dt. You're not literally multiplying here. It's really not literally 2t times dt as we approach it. If you use that more advanced graduate school level called infinitesimals, you could imagine it as a multiplication. And that's what Leibniz did back 350 years ago. But he was not being completely rigorous when he did that. It's not something you really have to worry about. Just do it. It gets you the right answer. And that's the way most scientists and engineers think about it. Just do it, and it gets you the right answer. So the t dt here gets replaced by 1/2 dw, and the t squared right there gets replaced by w, meaning we end up with the integral of 1/2 e to the w dw, which is an easy integral to do, to get 1/2 e to the w plus c. But then don't forget to replace w with t squared. And there we get the exact same answer we would have gotten by guessing. Now we're going to take the time for you to work on a problem on your own. And that's going to be part of class participation. And by 2:15 today, I'm going to have a link on Moodle for you to upload it. I'll send you an email reminder. I want you to upload a picture of your work. The integral I'd like you to do is the integral of x cubed sine of 1/2 x to the 4th. And to get full credit for class participation, I would like to see your substitution. I would like you to do it by letting either u or w equal something. And I want to see that work. Okay? Don't just guess. All right, let's work through this together now. Remember, some guidance is you want to let w, the substitution, or u if you prefer, be something in this integrand function whose derivative is also almost in the integrand function, almost meaning up to a multiplicative constant. And yeah, if you let your variable w, say, be 1/2 x to the 4th, the derivative of that will involve x cubed, which is right there. Let's let w equal 1/2 x to the 4th. Now, could you get away with just x to the 4th instead of 1/2 x to the 4th? Yes, you could. Though if you did, you might have to do another substitution to help you finish the problem. Find the derivative. Pretend to multiply both sides by dx. dw will be, bring the 4 down. 4 times 1/2 is 2. Subtract 1 from the exponent. Don't forget your dx. Okay, the dx is not here. It's here. And like the last example, we could try to solve for x cubed dx by dividing both sides by 2. Alternatively, you could put a 2 in here and compensate by multiplying by a half out front, excuse me. Either way is okay. If you do it this way, now that means you get 1/2 times the integral, the 2x cubed dx combined to give you a dw, and the sign of this becomes a sign of w. So you can just write this. And that integral is negative 1/2 cos of w plus c, but don't stop there. Get it back in terms of your original variable, in this case, x. Negative 1/2 cosine. What is w? It's 1/4 x to the 4th. And you can always check it by differentiation. And in the checking, you will have to use the chain rule. The substitution is the reverse process, essentially, of the chain rule. When you differentiate this, the derivative of negative cosine is actually positive sine. The negative sign goes away. And the derivative of 1/2 x to the 4th is 2x cubed. The 2 will cancel with the 1/2 and leave you with the original integrand that does not have the 2 and the 1/2 in there. That function right there. Okay, so this is correct. It's a little trickier, though. Let's make it yet a little trickier. Continuing to up level of difficulty. Say we're going to integrate cosine of square root of x divided by square root of x. That just feels trickier. What should you do when you encounter something like this? Well, if it's in section 7.1, which is about substitution, that means probably substitution is helpful. If it's on the test and I don't tell you what section it's from, then it's definitely not so clear. But sometimes, and this is a big point of emphasis for me, sometimes you just got to try something. You're not sure if it's going to work, which probably means you should do it on scratch paper. When you do these assignments, you should have some scratch paper handy that you're not going to turn in. The scratch paper is just where you try things and see if they work or not. And if you look at this, it seems like the only thing to try is W equals square root of x, say. X to the 1/2. Because there's a W there. W's here as well. Will we put W in both spots? That's not so clear. You do need to find dW in terms of dx. The derivative of x to the 1/2 is 1/2 x to the negative 1/2. Don't forget your dx. Here's where putting the dx is essential. I am going to need to replace dx with something involving dw. I've got this thing in there too, which seems to be really messing things up. Until you realize that this is the same as 1/2 times the square root of x. X to the negative 1/2 is the same as 1/x to the positive 1/2. In other words, it's the same as 1/square root of x. And that helps me realize that this part right there, the dx combined with really 1/square root of x, is almost what I want to replace with dw, though I do have to compensate for the 2. Now multiply both sides by 2 to say 2 dw is 1/square root of x dx. So this, what I circled up here, is going to get replaced by 2 dw. And this gets replaced by just w. It might feel like this may not work. You know, you might be feeling like, is this really going to work? Try it, see if it works. And the ultimate proof is in the checking. This integral is going to become 2 sine w plus c. Replace the w with square root of x plus c. Evidently, this is the correct answer. Check it. It's worthwhile to check it. Differentiate that with respect to x. You need the chain rule. The derivative of sine is cosine. I need to multiply times the derivative of the inside function, square root of x, which is x to the 1/2. Doing so gives 1/2 x to the negative 1/2. The 1/2s cancels with the 2. X to the negative 1/2 is the same as 1/square root of x. This simplifies to cosine of square root of x over square root of x. The original integrand. Yes, it worked. Question?
Why did you replace the bottom square root of x?
Yeah, it is true that does equal w. And you actually could replace it with w. Though if you did, you also want to replace dx with something. This equation would say dx could be thought of as 2 square root of x dw, but once again, square root of x is w. This is the same as 2w dw. So if I replace this with a w and dx with 2w dw, the w's would cancel and I'd get the same thing. Good question. Tricky, easy to make a mistake. Let's go on to yet harder problems. How about the integral of tangent theta d theta? Secant squared, is that the answer? No, it's not. The derivative of tangent theta is secant squared theta, not the antiderivative. It's not so clear what to do. If it's a trigonometry problem, if the function is a trig function, and it's not clear what to do, that's a big hint to try trigonometric identities and see if they help. In this case, use the definition of the tangent function as sine divided by cosine. And if you do that, it turns out to make it easier. And you can use a substitution. What should W be here? Sine theta or cos theta? Those are your two options. If you try sine theta, which you certainly could do, W was sine theta, you get dW to be cos theta d theta. However, the cos is not being multiplied by the d theta, you're dividing by cos, not multiplying. Dividing by cosine theta is the same as multiplying by 1 over cos theta. So that means that's a problem. And that means try W equals cos theta instead. Then dW, careful, will be negative sine theta d theta. And that means after you do the substitution, you need a negative sign in there, which you can put in front of the integral. And that, I hope you remember, is natural log. Somehow natural log is involved in this problem, amazingly enough. A connection between trig functions and logarithms? Weird, but true. Technically speaking, W could be positive or negative here, and so you do want to allow for that and put absolute value signs here. And that is important for some applications once in a while, so make sure to do it. But don't end there. Remember, you got to replace W in terms of the original variable. So we get negative natural log of the cosine, of the absolute value of the cosine theta plus C. And if you check this, I'll just do it in my mind here. When you differentiate natural log of something, you get 1 over that something, then by the chain rule times the derivative of the something. So I get 1 over cos theta is the something, times the derivative of cos theta, which is negative sine theta, but the negative sign in front cancels that negative sign, leaving me with sine theta divided by cos theta, which is the same as tangent theta. It would check. You can check things mentally. If it's helpful, write it down. Actually, you can't always check things mentally. Sometimes you really do need to write things down. Here's an even harder example. And this example is in the book. Integrate square root of 1 plus square root of x, all under the bigger square root sign. Yikes. It's definitely not clear that this is even possible. And yes, there are plenty of integrals where it's not really possible to find an antiderivative. Again, think Fresnel C and Fresnel S. However, it's not clear whether this is one of those or not. So let's try integrating it with a substitution. And the only two possibilities you could try for W would be, well, maybe square root of x, or maybe 1 plus square root of x. I'm going to do 1 plus square root of x so that this entire thing simplifies more nicely to just square root of W. This is the same as 1 plus x to the 1/2 power. Now differentiate, find dW. When you differentiate 1, you get 0, that goes away. The derivative of x to the 1/2 is 1/2 x to the negative 1/2 dx. So I could replace this square root, this big square root, with just square root of W. But what about dx? Evidently, I need to solve this equation for dx. It's the same as 1/2 square root of x dx. I guess that means I should multiply both sides by 2 times square root of x. dx would be 2 square root of x dw. But wait a minute. How is that helpful? If I replace dx with 2 square root of x dw, I still have an x in there. I don't want any x's anymore. Anybody got a guess as to how to get around this? Yeah, you could solve this equation for x, or maybe square root of x. And that's what I'm going to do. Take that equation and subtract 1 from both sides. Square root of x is going to be 1 minus, or w minus 1. And then replace this square root of x with w minus 1. Or u minus 1 if you're using u. Got that? That does work, right? W, by definition, is 1/square root of x, 1 plus square root of x. Subtract 1, that means square root of x is w minus 1. There's a square root of x, replace it. So now combining all these things, this integral does become simpler. Doesn't look much simpler, but it definitely is conceptually simpler. You get a square root of w for this entire thing. That becomes the square root of w. And then the dx gets replaced by this. Times 2 times w minus 1 dw. Now that integral doesn't look much easier, but it is. You can bring the 2 out in front. It's constant. And the square root of w can be distributed through the parentheses here to get, probably best to write it as w to the 3/2 minus w to the 1/2 dw. That make sense? Square root of w is w to the 1/2. Multiply it by 2, you'd add the exponents. 1/2 plus 1 is 3/2. And square root of w times 1 is w to the 1/2. And that now is a fairly easy integral to do. You need to do the reverse of the power rule. You need to add 1 to the exponent instead of subtract 1. Instead of multiplying times that exponent, you divide by it. Do the same thing with integrating w to the 1/2. Don't forget your plus c. Dividing by 5/2 is the same as multiplying by 2/5. Divide by a fraction, you got to multiply times its reciprocal. 2 times 2/5 is 4/5. Dividing by 3/2 is the same as multiplying by 2/3. 2 times 2/3 is 4/3. Wait a minute, we're not done. Replace those w's with 1 plus square root of x. So you get 4/5 times 1 plus square root of x to the 5/2 power minus 4/3 times 1 plus square root of x to the 3/2 power plus c. I'm not going to take the time to check that by differentiation. I would encourage you to do so. Should be able to do it in 5 minutes. You'd have to, in both cases, differentiate with the chain rule. And evidently, somehow, maybe like by magic, it should simplify to just that function. It should seem somewhat mysterious that it would do that. But if you don't make a mistake, it should. I think you will have to subtract fractions by getting a common denominator. And actually, the denominator would already be the common one. Okay. Question? Will I put problems like this on the exam? I don't think I ever have. Not this one exactly. I have put some other ones that are not quite as tricky as this one, but still somewhat tricky. We will do more examples next Monday. To end class today, I'd like to do a definite integral. And let's make the integrand the same example from Wednesday. 2x times 1 plus x squared dx. But I'd like to make this a definite integral, say from 0 to 3. When you do a definite integral with substitution, there's 2 ways it can be done. I'm going to show you one of the ways today and the other one on Monday. When you do your homework due Monday, do the way I show you today. And be careful to do it exactly like I'm doing it. There's good reasons for being careful here. What I want you to do for Monday's assignment is, instead of writing down your antiderivative first, which you could do by just guessing even, I want you to find the antiderivative using substitution on a separate line. In this case, let w be 1 plus x squared. Then dw is 2x dx. And so you get the integral of w squared dw to be 1/3 w cubed plus c. And that means the final answer here for the antiderivative is 1/3 times 1 plus x squared cubed plus c. Once you've done that, then use that antiderivative and the fundamental theorem of calculus to do the definite integral. I want you to show this work on a separate line, then use it back up here to write this. And then plug the numbers in. 3 squared is 9, plus 1 is 10. You get 10 cubed over 3 minus, plug in x equals 0, you get 0 squared is 0, plus 1 is 1, cubed over 3. 10 cubed is 1,000, minus 1 is 999. The answer is 333. For Monday's homework, do it this way. Do your indefinite integral with a substitution on a separate line, then use it. I didn't need the plus c, by the way, because when you use the fundamental theorem of calculus, you can take c to be 0 if you want. If you use some other value of c, it still works. And you still get the same answer, because when you subtract, the c effectively cancels. But you might as well just take c to be 0. There is another method here that I'm going to hint at, and I'll show you on Monday. The other method is to do the substitution right away with the definite integral. However, this is really important to me. People commonly make the mistake when doing that of keeping the limits of integration the same when they use the new variable. You should not. If you change to a new variable when doing definite integrals, you need to change the limits of integration if you're going to keep that new variable, and if you're going to get the right answer with that new variable. It's a little weird, but it is the way to do it. I'm not requiring you to do it now. Do it this way over the weekend. Next Monday, we'll talk about it, and then on next Wednesday's assignment, you'll do a few examples like that with the second method. All right, have a good weekend.